All right, class, welcome to homework number 5. We're going through the entire thing. And the reason why I wanted to go through it is to clarify a lot about the ideal gas law. And more specifically, the universal gas law constant. So, I have these units down here. They're the same as what I have up here for the universal gas law constant. And if you follow the units on that constant, you should get to the right answer every time. Every time. And the only reason why you would not get to the right answer every time is if you use different units. And so I want to talk about that for a few seconds. We have to have these specific units for every ideal gas law equation because the constant specifies it. So every time in volume it has to be liters. Every time atmospheres. Every time has to be in moles. Every time has to be Kelvin instead of degrees Celsius. And so let's go through each of these problems and let's differentiate. Let's go through them. Let's change up some units and we'll get to the right answer every time. So starting with number 1, at 0.210 moles of H2 gas exerts a pressure of 782 millimeters mercury at a temperature of 27 degrees Celsius. What would be the volume occupied by the gas? Okay. Well, I've already highlighted some of them here. So, 0.210 moles. Does it match up with the constant? Yes, it's there. 782 millimeters mercury. Does it match up? I don't see millimeters mercury in my constant, do I? I do not. So I have to find a way to change that up down the road. 27 degrees Celsius. Does that match up with my unit here? No, it's in Kelvin. I got to find a way to change to Kelvin. Okay. So we got a few things we got to change up. First thing is let's change up the pressure. So the pressure, if you remember back before spring break, we had a little bit of stuff about STP, right? Standard temperature and pressure. Well, if you remember, 1 atmosphere is equal to 760 millimeters of mercury. And so if I have 782 millimeters mercury, am I above? Am I below? Am I at 1 atmosphere pressure? Well, we can do some math and we can find that out. So if I do a little bit of math, and it's by the simple conversion process. If I have 782 millimeters mercury, I can, whatever I have I don't know, right? The unknown goes on top. Whatever I do know goes down below. You'll see that these units cancel out. And that's what we want. We want these units to cancel out, and we want to find ourselves in atmospheres. And so what you'll notice is that, again, millimeters mercury goes away, we're left in atmospheres, and hey, it aligns and it matches with one of the units in our constant, and that's what we need. And so you'll find that you're going to be at 1.02 atmospheres, and that's what we need, right? Next thing is going to be degrees Celsius. I think at this point we all know that we have to have it in Kelvin every time. There's never going to be a specific case where we have to have it in degrees Celsius. Maybe if it asks us to have it or have the answer in degrees Celsius, we have to use Kelvin first and then convert the answer in degrees Celsius. But right now, it always has to be in Kelvin. So we add 273 to 27 and we get 300 Kelvin. Now, we have moles, we have atmospheres, we have Kelvin. Look at this. We have atmospheres here, we have liters here, we have moles here, we have Kelvin here. Well, it's asking us to find the volume occupied by the gas. If we have 3 of the 4 variables here, the 4th variable is what we're going to find. And that 4th variable is going to be in units of liters, looking at the constant itself. So, let's plug it into our equation. Again, it's PV equals nRT. So, pressure, 1.02 atmospheres, times unknown volume, equals our mole amount, 0.210 moles, times the universal gas law constant, times temperature in Kelvin. And if we do a little bit of arithmetic, some algebra, if we isolate volume on its own side, we have to divide by 102, right? We have to get 102 on the right side. And so you'll find that this entire equation is going to equal volume. So 0.210 times 0.08206 times 300 divided by 1.02 equals V, and that should equal our answer in liters. And here's the thing about why we gotta have those specific units. If you take a little look here, right here we can get rid of a lot of units. So if we have Kelvin down below and a Kelvin above, guess what? Kelvin goes away. Now we have moles on top, we have moles down below. Guess what? Those moles go away too. And now what we have here. So we have atmospheres down below, we have atmospheres above. In reality, if you do a little bit of arithmetic, it's actually going to cancel out too. So atmospheres actually goes away as well. And guess what? The only unit left for us is going to be volume. So that's exactly why we need to have these units in a specific way. We got to have atmospheres, we got to have Kelvin, we got to have atmospheres. We got to have pressure, temperature, and volume in a specific way. That's what I'm trying to say. Okay. Number 2. If argon gas is collected over a cylinder in a volume of 629 milliliters at 998 atmospheres and a temperature of 35 degrees Celsius, what is the number of moles of argon? Okay, back to our constant, we got to look at these units. Do we have these units? Milliliters is not liters. So we have to convert milliliters to liters. The best way for us is to move the decimal place 3 spaces over. So 1, 2, 3. So 3 spaces to the left. You'll find that 629 milliliters converts to 0.629 liters. Now we have liters for our equation. That's awesome. Now what about degrees Celsius? Well, for that we got to convert Kelvin again, right? So add 273. And now we're at 308 Kelvin. Now, take a look at this. We have atmospheres, we have liters, we have temperature in Kelvin. The fourth thing we don't have is moles, and it's telling us to find the moles. So we are already set to go for our equation. Again, PV equals nRT. Let's plug it all in. 0.998 atmospheres times 0.629 liters equals some unknown N mole amount times 0.08206 times 308 Kelvin. And what you'll find is that if you want to isolate the mole amount here, you're going to have to divide this whole thing over. And it's going to be like this. So let me put those units in there. Whoops. Come on, here we go. So, now, here's what we got. We got 0.998 times 0.629 divided by 0.08206 times 308. Now, if I take a look and try to cancel out some of these units, we can cancel out Kelvin again. That's awesome. We can cancel out liters, because liters over liters, right? Cancels out. Atmospheres over atmospheres, they cancel out. And now we just have moles, right? Here's the thing about moles. If it's 1 over moles, it's just moles. And so that's going to be your answer in units, which is now our answer for number 2. 0.0248 moles. Don't forget, oops, what am I doing here? Of argon. So don't forget the units here. That's very important. Number 3, what temperature does 16.3 grams of nitrogen gas have a pressure of 1.25 atmospheres in a 25-liter tank? Okay, got a lot of stuff here. First things first, we have atmospheres, we have temperature. No, we have atmospheres, we have volume. And so, take a look at this here. Okay, we have atmospheres, okay, we have volume. Do we have moles? No, we don't have moles at all, right? And it's asking for temperature. And so this is what I kind of found some students to do. They just put in the gram amount as the mole amount, and that's not how we do that type of stuff. We got to do some conversions along the way to find moles. And so what we got to do, if you still have that mole map, if we want to get from grams into moles, we have to divide by the molar mass. And of nitrogen gas, that is a diatomic molecule, that's going to be 28 grams per mole, right? It's going to be N2. And so N2 is just 14 plus 14. There we go, N2. So how are you going to do that? Well, you take your 16.3 grams of N2, you're going to times it by whatever you don't know, the unknown on top, divided by the known on the bottom. You'll notice that grams will cancel out as a result. We're going to be left with just moles of N2, 0.582 moles. So that's what we want to begin with. Now, going with that, now we have moles, now we have liters, now we have atmospheres. We'll see moles, liters, atmospheres. It's asking for temperature, and with this constant, it's going to give us Kelvin, which is what we want. And so let's plug it all in. 1.25 times 25 equals 0.582 times R, 0.08206, times unknown value T. And if I want to isolate T on its own side, I have to divide all this over here, and it's going to look a little bit like this. And so let's do that same process, that same cancellation process, okay? Moles up top times moles down below, that one cancels out. Okay, that's good. Atmospheres divided by atmospheres. Atmospheres goes away. Liters times liters. Liters goes away. Now 1 over Kelvin is Kelvin, and that's what we want for temperature. And that's the only unit left for us, which is 654 Kelvin. Now I've noticed a lot of you did get this same process right. I love that. That's awesome. However, I think where something kind of went wrong was the molar mass here. Some of you did not have 28, you may have had 14, and that may have dropped down your temperature just a little bit, probably by half though. And I would say go back, double check it, do this same input for the molar mass, you should find 654 Kelvin. Some of us were like 320 something Kelvin, and that may have been because you only used 1 nitrogen instead of 2 nitrogens. So, okay, I got a few more minutes left. Okay, number 4, determine the pressure in a 125 liter tank containing 56.2 kilograms of oxygen at 21 degrees Celsius. Same process, we have to convert grams into moles, but in this case we have kilograms. So, what we have currently is 125 liters. We converted 21 degrees Celsius by adding 273, making it 294. And we don't know N because it's in kilograms, not grams. Again, you can't just add, you can't just say you have 56 moles. You got to do the conversion process. And our value is going to be, again, 0.08206. So, how to convert grams or kilograms into moles? First things first, kilograms, 1,000 grams equals 1 kilogram. And for oxygen gas, we have to consider is going to be O2 and not O. So this is going to be the wrong one. It's got to be the wrong one. This one is going to be the right one here. Oops. So you want this one here. Okay. Okay, what we're going to do now with this is that we're going to use our equation. I don't know why that's there. We have to convert kilograms into moles. So take 56.2, times it by 1,000. Therefore, it gets rid of kilograms, has grams on top. And keeping in the same process, times it by 1 over 32. So in essentialness, you're going to take 56.2 times 1,000 divided by 32. It's going to get rid of kilograms, get rid of grams. You're going to be in moles. Your mole amount is going to be 1,756.25 moles of O2. That's a lot more than 56.2, right? Now you have moles, now you got temperature, now you got volume. All you got to do is think about what we have here again. Oops. Oh, come on. There we go. What we have here again. Liters, atmospheres, moles, Kelvin. We have moles, we have Kelvin, we have liters. We got to find pressure. Pressure is going to give it to us in atmospheres in this case now. So, plug it into your equation. It'll be like this. You're going to do a little bit of algebra, right? Divide. You're going to be right here as your answer. Don't forget these units there. Oops. And then what you should find yourself in only atmospheres, which should be 339 atmospheres. Now, hopefully this makes sense. The key takeaway is make sure you have the correct units and always convert grams into moles before you do the actual PV equals nRT. Alrighty. Hopefully this makes sense. Give me a question or give me a comment if you have anything else, but have a nice day.